Hi all, welcome to the session on matrix decomposition. Matrix decomposition is also often referred to as matrix factorization. How to summarize the matrices and how matrices can be decomposed, how these decompositions can be used for matrix approximations. So these are what we are going to see in matrix decomposition. So first thing we need to understand is determinant of a matrix. Okay, we represent it like determinant det of A, or we can represent it using an operator, this pipe symbol. The determinants are defined only for square matrix. That is very much important. We can find determinant only for the square matrices. Okay. Then square matrix will be represented like this. Its dimension is n by n. Again, the equal number of rows and columns. The determinant of a square matrix A belongs to Rn by n is a function that maps a matrix A to a real number. Okay, this is what. So we have seen dot products or inner products of vectors. So what happened there? We are converting vectors into a real number. Okay, that was we have done in inner products or dot products. And this is a similar operation, that is a matrix is mapped to a real number. So we know that a matrix has many values inside it. Okay, depending on the dimension, we have many values in this, and these entire values have been converted to a real number, a single real number. That is what we are doing in determinants. Okay, so it is a mapping function that maps a matrix to a real number, a single value. Determinant of A is used to test the invertibility of A. That means whether an inverse for A is existing or not, whether this A inverse is existing or not. That is we determine by using the determinant of that matrix. So if the determinant is 0, we can say that there is no inverse exists for A. Okay, so if determinant of A is equal to 0, we can say that this A is not invertible. Or in other words, there is no inverse exists for A. If A is like this, if we take a 2 by 2 matrix over here, A11, A12 and A21 and A22, and how do we find out the determinant? We take the cross multiplication like this, A11 into A22. So we take A11 into A22 minus A12 into A21. Okay, so this is the formula we generally use for finding out the determinant of any matrix. For any square matrix A belongs to Rn by n, it holds that A is invertible if and only if determinant of A is not equal to 0. That we have seen in the last slide. And another two terms we need to understand is upper triangular and the lower triangular. And what is upper triangular? So when you look at this matrix, you can see that these diagonal elements 1, 4 and 6, and all the elements below this diagonal is zeros. Okay, so elements below diagonal are zeros. So and why it is called upper triangular? That means the upper elements are non-zeros. Okay, when you take this part, this entire part is non-zero. That is, the upper part is non-zero, so that is upper triangular. So this naming is given for non-zero values. So you understand in that way. And determinant of A is 1 into, how do you find out? You take 1 into this its cofactor matrix 4 4 6 minus 0 5, 0 into 5. So this is 4 into 6 minus, then in minus 2 into its cofactor matrix 0 into 6 minus 0 into 5, plus 3 into 0 into 0 minus 0 into 4. Okay, so then what is it? It is equal to determinant of A is equal to 1 into 4 into 6. Okay, so all the other terms are 0. This term is 0 and this term is also 0. So only remaining one is this part. 1 into 4 into 6. And what is that? It is 24. And it is actually the product of the diagonal elements. You can see the diagonal elements are 1, 4 and 6. And when you find the determinant of any upper triangular matrix, the determinant is just equal to the product of their diagonal elements. And let's have a look at the lower triangular matrix. And what is lower triangular? All the non-zero elements are in the lower part. Okay, so what are the diagonal elements? 1, 3 and 6 are the diagonal elements. And the all the elements below the diagonal element are zero, are non-zeros, sorry. And all the upper parts are zeros. Okay. And let's find out the determinant of B. It is 1 into 3 into 6 minus 0 into 5 minus 0 into 2 into 6 minus 0 into 4 plus 0 into 2 into 5 minus 3 into 4. Okay. And what is it actually? This these two terms are zeros actually. And on the first term, we have 1 into 3 into 6 and the remaining part is 0. Okay, so it is actually 1 into 3 into 6. And what is 1 into 3 into 6? Those are the diagonal elements. So in the case of lower triangular matrix also, we can see that the determinant of the matrix is equivalent to the product of their diagonal elements. So we can generalize this term for both for upper and lower triangular. If the matrix is triangular matrix, either upper triangular or lower triangular, the determinant of the matrix will be its the product of their diagonal elements. Okay, that is the general thing. The determinant of a triangular matrix is equal to product of diagonal elements. That is the summary from this experiment. And the triangular matrix is represented with the capital T. It can be either upper or lower triangular. And the determinant of this triangular matrix is equal to the product of TII. This symbol is product of symbol. Okay, product of I is equal to 1 to n TII. So what is TII? TII is the diagonal elements of the triangular matrix. Okay, so this represents the product of all the triangular diagonal elements. Okay, determinant is used to measure the volume. Okay, so it has another perspective like the volume. And in when it comes to two-dimensional, it is representing area. And when it goes to three-dimensional or higher dimensions, it will be representing the volume. So the determinant is used to represent volume also, or area. Okay, so in the case of two-dimensional, we have two vectors B and G. And when you complete the parallelogram like this, so this side is vector B again and this side is vector G again, and the determinant will give you the area of this parallelogram. Okay, so that is this area is calculated like this, determinant of BG. So BG is the matrix, okay, that represents these two vectors. Each column represents each of these vectors. So take the determinant of that matrix, we will get the area of this parallelogram. And when it comes to volume, when it comes to three-dimensional space, it is volume. So we have three vectors B, G, and R. So three vectors, let it be the basis. Three vectors. Then when we find out the determinant of the matrix representing B, G, and R, we'll get the volume of this parallel pipe. Okay. So determinant of BGR gives the volume of this shape. Okay. And for this is same for 4-dimension, 5-dimensional, or any high dimensional space. This determinant will give you the volume of the shape. Okay. Then let's take an example like this. Let R be 2, 0, minus 8, and G is equal to 6, 1, 0, and B is equal to 1, 4, minus 1. And let determinant A is actually RGB. Okay. And how do we represent it in the matrix form like this? It will be 2, 0, minus 8. That is vector R. 6, 1, 0 is vector G, and 1, 4, minus 1 is the vector B. And to find out the volume of this space, of this area, how do we find out? We will find the determinant of A. So let's find out the determinant of A. We get 186. Okay, so that is actually representing the volume. Then determinant of n by n matrices, we can use the Laplace expansion. Consider the matrix A belongs to Rn by n. Then for all j is equal to 1 to n, the expansion along column J, that is one method to find out the determinant through the expansion along the column, or we can do the expansion along the rows. Okay. Then if we are going for the first method, the expansion along the columns, we find out the determinant of A is equal to sigma k is equal to 1 to n minus 1 raised to k plus j, A of kj into determinant of A kj. Okay, so we this part is we already know minus 1. Alternate terms will be negated when you find out the determinant. And AKJ is we are taking values in one column. Okay, then find the determinant of AKJ. So that will be the cofactor matrix part. Then expansion along row J, determinant of A is equal to sigma k is equal to 1 to n minus 1 k plus j, A j k into determinant of AJ. Okay, these two methods we have already used in our high school classes. So this is like 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can either take 1 into its cofactor matrix minus 4 into its cofactor matrix, this one and this one, then plus 7 into its cofactor matrix, this. So it is along the rows. We are moving along the rows. Okay, so that is a row-wise method. Then column-wise method, we take this one. We take 1 into its cofactor matrix, minus 2 into its cofactor matrix, plus 3 into its cofactor matrix. So that is along the column. So that is column-wise expansion. So these are the two methods. We can go for any of these methods. So the answer will be the same. Okay. Then let's take an example. You can take this example and find the determinant of A. I am both using the column expansion and the row expansion, and just verify that these two are giving the same answer. Then the properties of determinants. First one is determinant of A, B. So if A and B are two matrices, and the AB is the product of A and B, and if you take the determinant of the product, it is equivalent to determinant of A into determinant of B. Okay, then determinant of A is equal to determinant of A transpose. So when you take the transpose of a matrix, there will not be any change in the determinant. Then determinant of A inverse is equal to 1 by determinant of A. Okay, so if you know the determinant of a matrix, in order to calculate the determinant of its inverse, it is just 1 by that value. It's reciprocal. Then phi from V to V, all transformation matrices A phi have the same determinant. Okay, so if we have a mapping function from one vector space to itself, all the transformation matrices will have the same determinant. That's a property we can make use of in machine learning. Then fifth one, adding a multiple of a column or row to another one does not change the determinant. Okay, so when we do it in row echelon form and all, that will not change the determinant of that matrix. Then multiplication of a column or row with lambda is equal, lambda belongs to R, that is with a real number, scales the determinant of A by lambda. In particular, determinant of lambda A is equal to lambda raised to n determinant of A. Okay, that means this n is the dimension of the matrix. If suppose A is n by n matrix, then this will be this is lambda raised to n. N is the dimension of this matrix. Okay, that means if you take a matrix A and you multiply it with lambda, that means you are going to multiply it with all the elements of A. Okay. Then when you take the determinant of this part, it is equal to lambda raised to n. That means if your matrix is 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, or we can just take a simple one. Just take this part 1, 2, 4, 5. When you multiply it with this is A, and when you multiply it with, we multiply with 1 and lambda into 2, lambda into 4, and lambda into 5. So 4 lambdas are here, right? Okay. So that is lambda raised to n, determinant of A. Then swapping two rows or columns changes the sign of determinant of A. Okay, swapping two rows or columns change the sign of determinant of A. Gaussian elimination method can be applied to find determinant of A. That means we can reduce the matrix into row echelon form in the upper triangular form. Then determinant of A is the product of the diagonal elements. So that is the best approach to find out higher dimensional matrices. Then the theorem says that a square matrix A belongs to Rn by n has determinant of A not equal to 0 if rank of A is equal to n. In other words, A is invertible if and only if it is full rank. So a square matrix has determinant of A is not equal to 0 only if its rank is equal to n. Okay. So we can say that if it is a full rank, then the A is invertible. That is its interpretation. Then the trace of a square matrix A belongs to Rn by n is defined as trace of A is equal to sigma I is equal to 1 to n Aij. Aii. That means A is the diagonal element. Okay. So trace is actually the sum of the diagonal elements. In the case of determinant of A, if it is a triangular matrix, we take the product of the diagonal elements. But here the trace is actually the sum of the diagonal elements. So it is sigma. Then the properties, trace of A plus B is equal to trace of A plus trace of B for all A, B belongs to R n by n. Then trace of alpha A is equal to alpha into trace of A, where alpha belongs to real numbers R, and for A belongs to Rn by n. Then trace of In, that is the identity matrix of size n, it is equal to n. That means in diagonal it will have n elements and all the elements are 1, and then the sum will be equal to 1 n. Okay, then trace of AB is equal to trace of BA for A belongs to R k by n and B belongs to R n by k. So since the multiplication is involved, the dimensions should match to do the multiplication. Okay. When this condition, this dimension condition is satisfied, then only we can do the multiplication. So it should be like this. Then only AB and BA, both the multiplications will be possible. And the trace of this product is equal to trace of this product. Okay. Then the trace is invariant under cyclic permutations. That is trace of A, K, L is equal to where A, K and L all the three are matrices, and it is equal to trace of K, L, A. So we are making the cyclic combinations K, L into A. So that's what we have done. Then we can say L, A, K. That is another cyclic combination. So for all these combinations, the trace will be the same. Okay, and there should be the constraints over the dimensions. The R should be alpha k, alpha by k, and it is k by L. K is k by L, and L is L by alpha. So there should be these kind of relation between the dimensions. Then only we can do the multiplication like this. Okay, then trace of x into y transpose is equal to trace of y transpose into x is equal to y transpose into x that belongs to R. Okay, then characteristics polynomial for lambda belongs to R and a square matrix A belongs to R n by n. P of polynomial, characteristic polynomial PA of lambda is equal to determinant of A minus lambda I, which is equal to C0 plus C1 lambda plus C2 lambda square plus etc. Cn minus 1 lambda raised to n minus 1 plus 1 minus 1 raised to n lambda n. Okay, where C0, C1, C2, etc. Cn minus 1 belongs to R, and C0 is equal to determinant of A, and Cn minus 1 is minus 1 raised to n minus 1 trace of A. Okay, so that is a characteristic polynomial. It allows us to compute the eigenvalues and eigenvectors, and we will see what the eigenvalues and vectors in our next lecture. And thanks for watching.